In this lesson, we consider some one-step synthesis problems using the carbonyl condensation reactions that we learned about in the previous unit. So for our first problem, we're going to consider how we would prepare this beta hydroxyketone from starting materials that contain 5 carbons or less. So remember that the constraints that I'm giving you in these sorts of problems are the number of carbons that you're allowed to start with, as opposed to what functional groups you're allowed to start with. So for our retrosynthetic analysis of this problem, the target molecule is a beta hydroxyketone, and therefore the reaction that you have to go into your toolbox and pull out is the aldol condensation. So this particular molecule will be made through an aldol reaction between a ketone enolate and an aldehyde. Okay, so let's look at this in a little more detail. So in order to do the retrosynthesis, you need to mentally break the C alpha, C beta bond, alpha and beta, of course, being defined relative to the carbonyl group that's intact in the product. We're going to turn the OH group at C beta into a carbonyl, and we're going to put a minus charge on C alpha. Okay, so this is a crossed aldol. That means that the enolate is not the same as that which is undergoing attack. We need a ketone enolate here, and more specifically, we need the kinetic enolate. Therefore, LDA is the appropriate base to be using for deprotonation. Okay, so then drawing our final answer in the forward direction, we start with our methyl cyclopropyl ketone as the starting material, and then the first thing that happens to it is we deprotonate it using LDA. Now note that I indicated that THF is the solvent for this reaction, because we need to indicate that that is an appropriate solvent to be using for a reaction with LDA. Then secondly, after the deprotonation is complete, we add in the aldehyde, and then finally we add aqueous acid to quench the reaction and give us a neutral product. Okay, so using the 1, 2, and 3 above and below the arrow gives you the order in which these reagents are added. They're not all added at exactly the same time, but they are all added to the starting material that comes before the arrow. Therefore, we can call this a one-step synthesis. Problem 2 now asks us to prepare this molecule with 3 rings, 2 of which are benzene rings and a ketone in the middle, from starting materials that contain 7 carbons or less. So if we analyze this, now we find out that the target molecule is a double alpha-beta unsaturated ketone. So that should be your hint that it is prepared through an aldol condensation under dehydration conditions. And in this case, we're going to find out that it is going to involve a ketone enolate adding to an aldehyde. Okay, so the more detailed analysis is we want to mentally break the entire C alpha, C beta double bond. We're going to turn each of the C betas, okay, we're going to do the same thing on both sides of the molecule. We're going to turn each of the C betas into a carbonyl, and we're going to put a negative charge onto C alpha. That's going to give us 2 molecules of benzaldehyde and the enolate of cyclohexanone. Now note that in my scratch work here, I drew a minus charge on both sides of the cyclohexanone. We're never actually going to form the structure with 2 minus charges. That's just there for scratch work. We're going to form 1 minus charge, and then later on in the reaction, we're going to form the other minus charge. But it just helps me in my analysis to realize that both of these carbons are going to have to become C minuses in order to form the carbon-carbon bonds. Okay, so this is one of those cases of a crossed aldol that will work with NaOH as the base, because the aldehyde has no alpha hydrogens, it's benzaldehyde, and the ketone is symmetric. It has just one type of alpha hydrogen. We don't have to worry about the ketone enolate adding to itself because the aldehyde will also be present in the reaction flask if we're using NaOH as the base. And aldehydes are much more reactive than ketones are as electrophiles in aldol condensations. Okay, so the final answer in the forward direction is we put both organic starting materials in front of the arrow because they are both present at the same time in the reaction flask, and then we're simply going to put excess NaOH above the arrow. We do want to indicate that there are two molecules of aldehyde that are present, a 2-to-1 stoichiometry between the electrophile and the nucleophile. Okay, and then we just draw our final product after the arrow. On to problem 3. In this problem, we have a beta keto ester, which is a sort of 1,3-dicarbonyl that we need to prepare from starting materials that contain 7 carbons or less. Okay, so the target molecule being a beta keto ester should clue you into the fact that it is prepared through a Claisen condensation between an ester enolate, and in this case, it's going to be a different ester. Okay, so for the Claisen condensation, we need to mentally break the C-alpha, C-beta bond. We're going to turn C-beta, which is a ketone in the product, into an ester in the starting material, and we're going to put a minus charge on C-alpha. That's going to be our ester enolate. Okay, note that I chose the methyl ester for the left-hand piece so that that piece does not exceed 7 carbons. It does not actually matter what ester I choose here because that piece is going to get lost as a leaving group in the reaction when the ketone enolate comes in and adds as a nucleophile. So this is also a crossed Claisen condensation. So LDA is going to be the appropriate base here. We don't have to worry about a kinetic versus thermodynamic enolate because ester enolates can only form on one side. So our final answer in the forward direction is we're going to take the right-hand ester. Okay, so this will be the propyl propanoate. We're going to deprotonate it using LDA and THF. Then we're going to add in the left-hand ester, the methyl, what would this be? 3,3-dimethyl pentanoate. And then those are going to react together in the Claisen condensation. You have to remember that under the basic conditions of the reaction, the hydrogen between the two carbonyls is deprotonated. We cannot stop that from happening. Therefore, to get a neutral product out of this, we have to add acid in order to put that proton back. Okay, so that's a problem involving the Claisen condensation. And then finally, problem 4 is to prepare the following 1,5-dicarbonyl from starting materials that contain 5 carbons or less. Okay, so when you see a 1,5-dicarbonyl as your target molecule, that should be your clue that it's going to be prepared through a Michael addition reaction involving an alpha-beta unsaturated carbonyl compound. In this case, the Michael addition is between a ketone enolate adding to an alpha-beta unsaturated aldehyde. Okay, so what do we want to do? When we do the more detailed analysis, we want to mentally break the C3-C4 bond. I just realized that I left a methyl group off of the first time that I drew this molecule, but the molecule that we are trying to make is actually drawn correctly in this analysis. Okay, so we're going to mentally break the C3-C4 bond. We're going to insert a double bond between C2 and C3, and then we're going to put a negative charge onto C4. Okay, so this is going to give us the alpha beta unsaturated aldehyde and the ketone enolate. Okay, so since this requires a kinetic enolate, LDA is going to be the appropriate base once again. And then the final answer in the forward direction is we start with our methyl isopropyl ketone, deprotonated on the less substituted side using LDA as the base to give us the kinetic enolate. And then finally, we're going to add in the alpha beta unsaturated aldehyde, which contains 4 carbons. And then in order to get a neutral product out at the end, this reaction is also going to have to be worked up with aqueous acid. Okay, so notice there's a difference between synthesis problems and mechanism problems. In synthesis problems, there are no curved arrows. We're not showing exactly what happens every step by step as the molecules react with each other. We're just indicating what we as a chemist put into the reaction flask, what reagents get mixed together, and what product gets out at the end. Okay, so these are one-step syntheses involving the carbonyl condensation reactions as carbon-carbon bond-forming reactions. In the next video, we will increase the complexity one more step and start talking about multi-step syntheses with carbonyl condensations, specifically the aldol condensation, as the key carbon-carbon bond-forming step.